Welcome to a screencast on phase diagrams. The objectives of this screencast are to describe the construction of a phase diagram, including the meanings of triple point, critical point, and supercritical fluid, and to interpret phase diagrams, including the conditions for stable phases, occurrence of phase transitions, and locations of triple and critical points. Now, in a previous screencast, we saw the vapor pressure versus temperature relationship, and liquid and gas are separated by this liquid-gas equilibrium line. So this, in a sense, is already, we've seen a phase diagram. This shows the conditions of temperature and pressure under which we have liquid phase, gas phase, or liquid and gas in equilibrium. Now, we can expand this to a phase diagram for a substance dealing with all phases. So again, we're going to make a temperature versus pressure graph. And again, from experimental data, we'll have a line that divides the liquid and gas phases. So this is the liquid-gas equilibrium line, or the vapor pressure line. There's also a line separating the liquid from the solid phase, and a line separating the gas from the solid phase. So substances that have pressures and temperature in this region will be solid. In this general region, they'll be a gas, and in here, they'll be a liquid. Now, again, as noted, this line is the liquid-gas equilibrium line. This one is the solid-liquid equilibrium line, and here we have a solid-gas equilibrium line. So this is kind of a typical, relatively simple phase diagram, 3 phases, solid, liquid, gas. And this, in fact, is roughly what the phase diagram for water looks like, or at least part of it. Now, there's a couple features worth pointing out. First of all, the boiling point and the melting point. Now, these are normal boiling point and melting point. As discussed in a previous screencast, under normal atmospheric conditions at sea level, or 1 atmosphere, when the vapor pressure of the liquid equals the external pressure, we have boiling. So this point of pressure and temperature corresponds to normal boiling point, and this temperature is the normal boiling temperature of the substance. Similar idea, here would be the normal melting point of the substance, and of course, we can have melting and boiling points at different conditions with higher or lower pressure, and they will similarly be points on this line or on that line. Now, there's a point where the solid-liquid, liquid-gas, and solid-gas equilibrium lines all meet, and that is what's called a triple point. And the triple point, here's an illustration of it for water, and it's called the triple point because we have solid, liquid, and vapor, all 3 standard phases, all coexisting at a very specific temperature and pressure. For water, this is barely above 0 degrees Celsius, 0.0098 degrees Celsius, and very, very low pressure, 0.0060 atmospheres. So if we have exactly that temperature and pressure condition, we have ice, we have liquid water, and we have gaseous water, all coexisting in equilibrium. For a different substance, it'll also have a triple point, but it'll be a different temperature and pressure condition for that. Now, another thing that happens, you'll notice that the solid-liquid line extends, just kind of keeps going here. It'll go off the chart, whereas the liquid-gas line actually stops. And the point at which that stops is called the critical point, and it's kind of an unusual situation. The temperature at which that occurs, where the critical point is the critical temperature. Similarly, we have a critical pressure corresponding to that point. And beyond that, when we have temperature and pressure beyond the critical point, we have something that's called a supercritical fluid. And it's sort of a strange substance. It's a fluid, like gas and liquid are both fluids, but it's not really quite a liquid, it's not really quite a gas, and it has some interesting properties. And we'll take a look here at a demonstration of a supercritical fluid. This is going to be for carbon dioxide, and this is a video from the University of Nottingham. So what we have here that Dr. Calladine is showing is a cell containing liquid carbon dioxide and gaseous carbon dioxide, and he's wiggling it to show that this is a live picture. The cell is down here, and what he's going to do is heat this up and see what happens. So he's heating it up. So let's take a look at what happens, and you can see some bubbles forming as the liquid's starting to get ready to boil. And notice that the phase boundary is starting to disappear between the liquid and the gas. The formation here is a supercritical carbon dioxide. It's either, you could look at it as a really dense gas, or it's not quite a liquid. It's something sort of in between, and it has unique properties. And what he's going to do now is show you what happens when we let things cool down. So now he's turned off the heat, he's letting it cool down. Here is our supercritical carbon dioxide. And very quickly we have this sort of snowstormy effect where liquid suddenly starts forming in the bottom of the cell. So we have gas up above and this sort of snowstorm of liquid forming. Again, you can see it's live. There's not as much liquid yet because it's still condensing. And so now we have two separate phases, a liquid phase and a gas phase, like we started with. But and our supercritical fluid has now reseparated into those two distinct phases. So here is a more detailed phase diagram for water. It shows the gas phase here in brown, liquid phase in sort of purple, and ice phase solid in, I guess, a bluish color. The triple point corresponds to the temperature and pressure where all three phases can coexist. The critical point, which for water is about 374 degrees Celsius and 22,000 kilopascals, or about 22 atmospheres or so. Beyond that temperature and pressure, we have a supercritical fluid. Any temperature pressure point within here means we have a gas. Any temperature pressure point within there is a liquid, and within here is a solid. And then, of course, if the temperature pressure conditions change from, let's say, here to there, you have the phase change of solid turning into liquid or melting. So anytime you cross this solid liquid line, that's either melting going this way or freezing going that way. Similarly for this line, this liquid gas equilibrium line, if we cross it, we're vaporizing, going to the right. If we go to the left, we're condensing. And then this line here between solid and gas, crossing left to right, is sublimation, and from right to left is deposition. Notice that the solid liquid line slopes to the left or negatively, and what this means is if you increase the pressure, you actually have a solid becoming a liquid, and this can be demonstrated. Here's a block of ice, and we've got a couple of weights on a wire, and if you hang this wire across the block of ice very, very slowly because of the increased pressure, the solid underneath the wire turns to liquid, and very, very slowly this wire actually cuts through the ice. It actually freezes back on top, and so the wire can very slowly cut through the block of ice and drop out the other side, but the block itself stays frozen. This is very unusual for increased pressure to take a solid and make it a liquid. Usually when we increase pressure, the other thing happens, the liquid becomes a solid, and this happens when we have a negative sloping solid liquid equilibrium line. So here is the phase diagram for CO2. Notice it's fairly similar to water's, but it has a positive sloping solid liquid line, and here are shown vaporization, condensation, melting, freezing, and sublimation, deposition as the phase changes, and triple point and critical point are shown as well. And one more thing to note, sometimes phase diagrams are shown with the units on one axis in a linear fashion. So here the temperature is fairly linear, but it's also pretty common to have the units on one axis to be not linear but logarithmic, and sometimes both are, and sometimes that leads to fairly strange looking phase diagrams, but it's just sometimes that's what's necessary to do. So for example, here to go from low to very high pressure and get that all on one graph, we have a logarithmic scale here, and so some of these lines end up being curved. And that is it for the phase diagrams screencast.